Look closely at the seams on a Starship prototype from a few years ago, and you'll see something almost embarrassing for a company building the most ambitious rocket on Earth. Thick, lumpy welds running along a hull that looked more like a backyard science project than a spacecraft. Now look at a Starship rolling out of the factory today. The seams have practically vanished, the surface smooth, almost mirror-like in places. Nothing about the underlying material changed. What changed is something most people never think about: welding, and the story of how that process went from rough soda can seams to some of the cleanest welds in aerospace is far more interesting than it sounds. Starship's body is, at its core, just a giant metal cylinder, but making that cylinder smooth, strong, and capable of surviving launch, the vacuum of space, blistering re-entry heat, and repeated landings is a far different challenge. Today's vehicles have cleaner lines, smoother surfaces, stronger joints, and far fewer visible flaws than the prototypes from just a few years back. So how did the process improve so dramatically in such a short window of time? The answer involves a surprising amount of trial, error, and a few genuinely clever engineering leaps. Back in the earliest days of the program, the infamous water tower era, engineers relied heavily on flux-cored arc welding, or FCAW, a tubular wire electrode fed through a welding gun with a flux-filled core. When the wire touches the metal, an arc forms, generating heat that melts both the wire and the base metal so they fuse together as they cool. The wire itself melts into the joint, and the flux core shields the molten metal from atmospheric contamination, preventing oxygen and nitrogen from weakening the weld as it solidifies. FCAW became popular across heavy industry for good reason. It's fast, productive, and doesn't demand complicated equipment. Valuable when you're building enormous steel structures quickly while constantly redesigning them. But it came with trade-offs: significant spatter, larger heat-affected zones, and more distortion, since heat poured into the steel expanded and contracted the metal as it cooled, making precise shapes harder to hold. The result was a rocket that looked, frankly, rough around the edges. Thick seams, visible inconsistencies, and weak points that required rework. If early prototypes looked assembled in a hurry, that's because, in a sense, they were. From there, the improvements stacked up quickly. Engineers switched to 304L stainless steel, which welds more cleanly and holds up better at low temperatures, and adopted Tip-TIG welding for deeper penetration and far less warping. They also started using larger steel sections per ring, cutting the total number of welds needed, because the best weld is the one you never had to make. Another leap came from planishing. After welding, a massive custom-built machine hammers and compresses the weld area. It sounds violent, but the effect restores strength to the metal and erases the scarring left behind by the weld itself, a big part of why newer Starships look so much sleeker than their ancestors. Then came what might be the most striking shift of all: laser welding. Unlike traditional methods that spread heat across a wide area, laser welders concentrate enormous energy into a pinpoint spot, producing a deep, narrow weld with minimal heat input and a remarkably clean finish. Engineers weren't immediately sold on the idea. Handheld laser welders looked more like sci-fi props than serious industrial tools. But that skepticism faded fast. The first experiments used lasers for tack welding, the small, temporary joins that hold parts in position before final assembly, and laser tacks came out smaller and cleaner than traditional TIG tacks almost from the very first test. Then came the real surprise. As testing pushed further, engineers found the lasers could create full penetration welds straight through stainless steel while leaving only a tiny bead on the surface, upending the old assumption that a strong weld has to look big and bulky. The technology improved further once handheld laser systems incorporated wire feeders. Early autogenous welding, without filler material, was extremely sensitive to the slightest shift in hand movement. Once filler wire entered the picture, it naturally guided the torch along the joint, making the process far more stable and repeatable. The moment laser welding became a genuine production tool rather than an experiment. Perhaps the biggest win, though, was less warping. Traditional MIG and TIG welding pours large amounts of heat into the metal, and as steel heats and cools, it expands and contracts, distorting the structure. A minor annoyance on a car body, but a serious problem on a 50-meter rocket that has to survive launch, re-entry, and repeated reuse. By concentrating heat into a tiny spot, laser welding sharply reduces that distortion, keeping the finished structure far closer to its intended shape. Some tests produce numbers that would make any welding engineer grin. Certain laser-welded joints proved so strong that the surrounding stainless steel failed before the weld did, meaning the joint was no longer the weak point, the base metal was. That's when it became obvious these tiny laser welds were making the entire vehicle stronger, lighter, and easier to build, all at once. Once the technique was refined, the next step was automation at scale, with robotic welders and specialized tooling turning out vehicles faster and with far more consistency than before. Every weld inspected via X-rays, ultrasound, and dye-penetrant testing to catch defects before they become real problems. Welding tells only part of the story, though. The other half belongs to Raptor, the engine that actually makes Starship more than an extremely expensive piece of stainless steel plumbing. Building it is, if anything, even harder than building the hull. The precision requirements are so extreme that critical components still rely on manual welding, since automated systems simply can't hit the required tolerances. Engineers on the program describe situations where the smallest imperfection could ruin a part worth hundreds of thousands or even millions of dollars. No pressure. Part of the difficulty comes from the materials themselves. Raptor relies on advanced superalloys engineered to survive some of the harshest conditions imaginable. Inside the engine's oxygen-rich turbopumps, pressures can climb to roughly 800 atmospheres. These alloys descend from Inconel-based materials, prized for retaining strength at extreme temperatures, but notorious for being brutally difficult to machine, since each cut tends to make the metal harder still. The payoff is worth it. At extreme heat, these alloys form protective oxide layers that resist corrosion and hold their strength long after ordinary metals would fail. Engineers also turn to advanced casting techniques for some of Raptor's most intricate parts, pouring molten metal into precision molds to create shapes too complex or expensive to machine from solid blocks. And as the engine evolved from Raptor 1 to Raptor 2 and now Raptor 3, simplifying manufacturing became a central priority. Fewer parts, more welding built directly into the structure, and bolts and flanges replaced with permanently welded assemblies. Raptor 3 pushes that further, tucking pipes and sensors inside the engine itself. Fewer parts mean fewer welds, fewer leaks, and an engine that's easier to reuse flight after flight. There's also a manufacturing tool that barely existed in aerospace a couple of decades ago: metal 3D printing. Instead of cutting material away from a solid block, engineers grow components layer by layer from a digital design, enabling internal channels and cooling passages traditional manufacturing can't produce. Injectors and turbopump elements benefit enormously, since injectors carry delicate pathways that deliver fuel and oxidizer with extreme precision, while turbopump components must endure punishing heat, pressure, and rotational stress. Even so, costs climb quickly at scale, so plenty of Raptor's parts still rely on more conventional methods. In many ways, the evolution of Starship's welding is the story of the whole program in miniature. Early hardware was rough, occasionally messy, and prone to spectacular failure. But every failure exposed a weakness, and every weakness led to a fix. Those clean, almost invisible weld lines on today's vehicles aren't just cosmetic improvements. They're physical proof of thousands of lessons learned, countless design iterations, and a relentless drive to turn a giant cylinder of stainless steel into a vehicle built to fly to the moon, to Mars, and well beyond.